So let's start talking about this situation. A train is moving along a track. Sorry. At a steady rate of 75 miles per hour. Steady. Okay? From 7 a.m. to 9 a.m. What is the total distance traveled by the train? We can do this. It's not even calculus. All right? All we need to do is use the formula distance equals rate times time. So we say distance is 75 miles per hour times 2 hours. Now, you've got to keep units because they're going to help you figure out whether or not you're doing it right. So the hours will cancel. You end with miles. I'm looking for distance. That makes sense. So it's 150 miles.
Do we have to keep the units or can we just put them down?
I would in the beginning to know what you're doing. Okay. Now, let's take a look at how this relates to a graph. Here you have velocity versus time. The velocity of this train is 75 miles per hour. It's steady, constant, 75 miles per hour. So your y is 75. Okay? Now, we're looking at this from 7 a.m. to 9 a.m. Right? So this is the time interval. So let's talk about distance then. How did we find distance? Distance was rate times time, correct? Okay. How much time did it take for this to happen? 2 hours. What is the rate? 75 miles an hour. What shape is that shaded region? It's a rectangle. So when I multiply 75 times 2, what of the triangle am I finding? The area, right? So by finding the area of the rectangle, that gave me the distance that the train traveled. Okay? So, the distance traveled is exactly the area of the rectangle. And now, what is the base? The base is the time interval. The height is the velocity. Okay? All right. How often, though, is the train just traveling at the same speed? Not very often. A lot of times, the velocity is going to vary. Okay? If the velocity is varied, then suppose it looks like this. Now, if we go from 7 a.m. to, let's say 9 a.m., okay, look at this region. It's no longer a rectangle. But what does that area represent? Okay, so it's some irregular shape. Now let's say there was a way to find the area of that irregular shape. Would the area still give the distance? Yes, it would. Okay? In fact, both Isaac Newton and Leibniz, another mathematician, thought the same, that the area under velocity time graphs would provide distance. So They figured out a way to do it. So let's get that same exact curve. And let's get that same exact interval. From 7 to 9. You know what they thought of doing? They said, what if I could divide that region not into a rectangle, but many rectangles. 1, 2, like this. Okay? Now, if I could find the area of each rectangle and add them up, would that give me a good approximation for the area underneath? Yes, it would. The point now is, how do I do that? There's millions of them. I drew a very small number of rectangles. Potentially, or ideally, you would draw an infinite number of rectangles. You know, but that's how it would look. So now, let's take a look at some of these. Take a look at this one, and let me just draw the edges. Do you see that? So, each rectangle has an area of length times width. Okay? So, what we're doing here is partitioning into many tiny subintervals. We don't divide into rectangles, we divide into tiny subintervals. We partition. Okay. Here we go.
They're essentially the same thing. They're the same thing. Like, even though they're called
right.
Actually just a total.
Right. So now take a look. The width of each rectangle is the length of each subinterval. So this is the width. Okay? Now, the height is the function's value at each endpoint. Here's the big idea. The height now, here, it's f of x at that point. So, if this is the point x5, the height of that rectangle is f of x5. So, do you see what we're doing? The width, okay, let's say this is a distance of 2, and I divide it into 10 rectangles. How wide is each one? 2 divided by 10. How high is each one? You figure out what the x value here is, plug it into f, and you get the height. When we do the next example, you'll see what I mean. What you need to know now is these two. Okay? Commit these to memory if you have to. That the width is the length of the rectangle. The height is the function's value. Now, I can draw rectangles underneath. And the way I do the rectangles matters. So for example, take a look at this curve. I could do a rectangle here, right? And I could take, so how am I going to do the top? I could either do it this way, right? Or I could do it this way. Do you see what I mean? I could either close the top from left to right or from right to left. What happens if I did it from left to right? Look, I have a little bit that it's unaccounted for. What happens if I do it this way? I get a little bit of extra. And then another way to do it is, here it is. I could find the midpoint and close it off at the midpoint. Okay? Each of these, they're called LRAM, left rectangle approximation method, RRAM, right rectangle approximation method, or midpoint RAM. Okay? All right. So let's estimate the area of this. The curve we're looking at is f of x equals x squared. We're going to go from 0 to 3 with 6 subintervals. So you need to know all of that information. Okay? Now, if you're going from 0 to 3, that's a distance of 3. You're dividing it into 6. So how big is the base? B is 3 over 6, 1/2. Okay? So that means from 0 to here, it's 1/2, and then 1, and then 1.5, 2, 2.5, which is 5 over 2 and 3. You see that? All right. Now, let's do LRAM. So we're going to take the left end point as the height for each triangle, for each rectangle. How many rectangles? 1, 2, 3, 4, 5, 6 is that tiny little one underneath. All right, so let's do this one. LRAM is going to be, okay, we're going to do the first rectangle. The base is 1/2. How much is the height? It starts here. The left end point is at 0, so 0 squared. Plus the second rectangle. It's 1/2 times, how much is the height? 1 over 2 squared. So look, I'll do it this way. This is the first rectangle. Okay? So it's 1/2 times 0 squared. Okay, so you see how the red is the first rectangle. What's the left end point of the rectangle? X equals what? 0 squared. Alright? And then let me do another color. Let's do blue for this one. That's the base is 1/2. The height is the left end point, 1/2 squared. Now let's do the next one. Oh, 3 over 2, yes. I said 1.5. Okay, so the purple one, how much is the base? 1/2. And then the height is going to be the left end point, 1 squared, plus now the green one, the base is 1/2 times 3 over 2 squared. And then I'll do this one in black. 1/2 times 2 squared. And then the last one, 1/2 times 5 over 2 squared. The base, it goes from 0 to 3. Right, it's 3 units. And then we divide it into 6 subintervals. 3 over 6 is 1/2.
So it's always the second number over the interval?
No, it's the interval. If it was from 1 to 5.
Oh, I understand.
So this, you plug it into the calculator, you get 6.875. Okay, now we're going to do, now we're going to do the right end point. So again, this is 0, 1/2, 1, 3 over 2, 2, 5 over 2. Now, again, the first rectangle, it's 1/2 for the base. And what's the height? Not 0. Now we're going to do the right end point. 1/2 squared. Okay, so this is RRAM. Equal plus 1/2 times what squared? 1 squared. 1/2 times 3/2 squared. 1/2 times 2 squared. 5/2 squared. Now don't get carried away. Do as many rectangles. Do as many as you have rectangles. We plug it in. 11.375. Does it make sense that we got a bigger number? Yeah, because this way you're overestimating. Okay, Karen. Now we're going to take the midpoint of each rectangle. So if each rectangle, if this one goes from 0 to 1/2, what's the midpoint? 1/4. So the midpoint here is 1/4. I'll get you in a sec. Here, it's 3/4, 5/4, 7/4, 9/4, and what do you think? Yay. Oops, I did pi. 11/4. Okay, so MRAM base is 1/2 times what squared? Right. Plus 1/2, 3/4 squared.
Why aren't you using 1/4 as your first?
This is the length of the base. The length of the base is still 1/2 because we went from 0 to 3, divided it into 6, so we get 1/2. So plus 1/2, 7/4 squared, 1/2. Now, this is going to be 8.938.
What's the number, the next one over from 7/4?
9, 7, 9, 11.
This was the middle one, the most accurate.
So that one was, a baby one. Okay. So you have a function that looks like this. Y equals 1/2 x squared. And the region you're looking for is enclosed between 1/2 x squared and the x-axis from 0 to 4. Okay, so let's graph this. 1/2 x squared, what shape is it? Parabola. Let's quickly put some points in here. So when x is 0 and you plug it into 1/2 x squared, right? What do you get? So when x is 0, y would be 0. When x is 1, y would be 1/2. When x is 2, y would be 2. 3, y would be 1/2 times 9, 9/2. And then when x is 4, 8. Okay, so 0, 0, 1, 1, 2, 2.
No, it's 1.
1/2.
We have a calculator, right?
I feel like a stake through my heart right now. We didn't use a calculator for any of this. So we graph this. Okay? This is y equals 1/2 x squared. The region I want is R enclosed between the graph in purple, the x-axis and it goes from 0 to 4. So you see that region? That's the region. Now, we're going to partition R, so this is R, into 4 subintervals of equal length. So the base is going to go from 0 to 4. That's 4 units divided by 4, 1. So basically they're going to look like this. Okay? Yes. Okay. So LRAM is going to be 1. So you see how, you remember what I said? When the base is all the same, I don't have to write it each time. So for the next one, we'll do that. So how about here? It'll be 1 times what? So, right, 0 plus, okay, so now look, this is rectangle 1, 2, 3, 4. If we're doing left RAM, for the second rectangle, it's going to be, it's going to be half of 1 squared, right? Okay, so here's how we do it. You see how I did this chart before? Suppose you didn't do the chart before. You just estimated. Now, for each point, you could just do the base value and then the y value, the y value, the y value, the y value. Okay?
Is there something like 1/2 of 0 squared equals like 1/2 of 0?
Yeah. So now here, it'll be half of, so for the third triangle, what is it going to be? 2 squared, so that's f of 2, plus 1/2, 3 squared. You're plugging it in to the, so for each one, for each rectangle, I'm plugging in the left endpoint into y. Okay? Well, it's 1/2 x squared. Right, so what I'm saying is normally we don't do this ahead of time because it wastes time. Normally we're going to have the graph drawn up. You just estimate the graph and we do it like this. Okay? When we put it all in, this is a cute little 7. Now we're going to do the right RAM. So it's 1 times, so you do the base times each height. Okay, so when I did it before, I got 7.
Because it's 1/2 plus 0 plus 4.5 plus 2.
It's 0. We're going to take the right endpoint. So for triangle 1, the right endpoint is 1. So it'll be half 1 squared plus half 2 squared plus half 3 squared plus half 4 squared. And that'll give us 15. Now for the midpoint, it's going to be the base times, now the midpoints of each one. So what are the midpoints? 1/2, 3/2, 5/2, 7/2. Okay? Yeah.
I'm really confused about why everything is mostly over 1/2. So that's a base.
Because each rectangle has a base of 1, right? So you have to do, look, you have to do base times height, base times height, base times height. 1 times height, 1 times height, 1 times height. I could just factor out the 1. So look here, right? You see how there is a half for each term? Each of these halves is the base. I could just factor them out and write it once. Okay?
Is the base always going to be 1?
The base is always the length of the interval divided by however many rectangles you have. In this problem, yeah. No,
I think her question was that the function is 1/2 x squared, and we're always plugging into that, and that's what it goes to 1/2.
are you talking about the 1/2 or the 1? Because you said 1. Oh, I heard 1. Yeah.
Aren't there technically 5 rectangles though? Because you're still counting the first one.
No, hang on. Let me finish this one. So now these are the midpoints. Half x, look, half x squared plus half x squared plus half x squared. And we get 10.5. All right?
Oh, is that what we're talking about?
Yeah. Yes. It shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1 with LRAM and RRAM. Okay. 10 subintervals of length 1. So how much is each base going to be? 1. It goes for 10 seconds. 10 subintervals. And this one, it tells you length 1. So base is 1. Now, sometimes you're going to be given a table, sometimes you're going to be given a graph. So remember, how does a table relate to a graph? Right. And also, so it's 0, 1, 2, 3. So here, 0 is 0, and 1 is at 12. So, if I have a triangle like, a rectangle like this, if I do LRAM, right, I'm going to start with the very first y value and go over. But if I do RRAM, which one am I going to start with?
The 1.
The 1.
So you don't have to plug it into that function.
Right, you don't have to plug it into a function. But the trick here is, when you're doing LRAM, you start with the very first one. When you're doing RRAM, you start with the second one.
That's the trick for all of them.
Yeah, that's the trick for the table. Right? Yeah.
And when you're doing the
MRAM, you have to calculate the middles. In this case, it's hard to do because, but you're not given y value, so you can't do it for this.
Can you divide the y value now?
No, I mean, you would, because you don't know how it's progressing. So, for LRAM, start here. For RRAM, start here.
in LRM, you always like stop one before.
Yeah. You always have to have as many terms as you have rectangles. So 10 in this case. So LRAM, it's going to be the base times height 1, height 2, height 3, height 4, height 10. Okay? Height 1, height 2. No squared. You're given them now.
Oh.
Yeah.
Wait, why aren't we multiplying? Oh, so the reason you're multiplying by 1 half and squaring it is because there's these equals that we can.
Yeah, the function was given to you, and you were trying. I got caught into it. We were squaring it before because we were plugging it into the function in order to get the y values. So you're not always going to be.
That's why on the top you wrote like f of 1.
Right, you're not going to be squaring it all the time. You're going to do whatever operation the function tells you to do. So where am I? 0, 12, 22, 10, 5, 13. Yeah, and this is 87. Now, we're given units here, explicit units. So for distance, what are the units going to be? Inches. So for RRAM, it's going to be the base times 12 this time, 22, 10, but one more in the end. Yeah. I mean, in this case, but not. Yeah. Wait, hang on. Let me finish what I need to say. So, do you realize how, Julian, we were talking about this before. This is a totally different type of function where LRAM and RRAM happen to be equal to each other. So, based on the scenario, the situation, or the function, we choose, LRAM, RRAM, MRAM. Sometimes one is better than the other. Okay, I'll take a question and then I have something else to say.